just 120 light-years away in the Leo constellation, the James Webb Space Telescope has made a discovery that could rewrite everything we thought we knew about life in the cosmos. Astronomers have detected a planet with a surface temperature locked at 120 degrees Celsius, perfect for life as we know it. Even more shocking, its atmosphere carries the unmistakable chemical fingerprints of living organisms. But that's not all. The evidence is overwhelming. Scientists are 99.7% confident in their results. This could be the clearest proof yet of a truly habitable exoplanet, our strongest candidate so far. Could this be the first undeniable sign that humanity is not alone in the universe? If this holds true, then history changes today. We are no longer the only ones, so join us on this extraordinary journey. Hit that like button, subscribe, and turn on the notifications, because this is just the beginning. The search for life has entered a new era, and you're part of it. Are you ready? Let's dive in. Right now, while you're watching this video, maybe billions of living beings could be breathing at a distance of 124 light-years. According to newly made discoveries on a planet 124 light-years away, the greatest discovery in human history may be happening. And this inevitably brings the following question to mind: are we no longer alone in the universe? The date of April 17, 2025 was recorded as a day written in golden letters in the history of space exploration. The data published by NASA on this date contained findings that caused not only the scientific world, but all humanity to question our place in the universe. The new evidence obtained about the planet K2-18b shows with a probability of 99.7% that this distant world could host life. This incredible figure is almost used in today's terms as a guarantee. So what does this mean for us? One of the most important clues in the search for life in space is the presence of chemical substances called biomarkers. The dimethyl sulfide, DMS, detected in the atmosphere of K2-18b is a gas that on Earth is produced almost exclusively by living organisms. That sea smell which we feel relaxed when we smell it by the seaside is created because of this gas. Hold on tight. Now this sea smell is not only on our world, but also coming from a planet 124 light-years away. Now stop for a minute and think. The concentration of this gas in the atmosphere of K2-18b is 1,000 times higher than on Earth. Scientists could not hide their astonishment at this figure. Because dimethyl sulfide is an extremely unstable compound, destroyed in just a few days by sunlight and oxygen. This means the following: if it is present in such a dense amount in the atmosphere of K2-18b, it must be continuously produced. The method by which the James Webb Space Telescope carried out this discovery is a perfect example showing how far technology has advanced. I am sure now this is passing through your mind. How can we analyze the ocean's smell in the atmosphere of a planet 124 light-years away? Even though this seems impossible to our eyes, the final point reached by advancing human technology is exactly at this level. The power of science makes this possible. The telescope watches as the planet K2-18b passes in front of its star, observing the starlight filtering through the planet's atmosphere. Different gases in the atmosphere absorb certain wavelengths of light, leaving behind their unique fingerprint. With this method, we can resolve the chemical composition of an atmosphere trillions of kilometers away, as if analyzing it in a laboratory. In the scientific world, for discoveries to be acceptable, they must surpass certain reliability thresholds. These criteria, called sigma values, show how reliable a finding is. Sigma, 68% reliability. Our first observations were exactly at this level. 3 sigma, 99.7% reliability. The current K2-18b data has reliability at this level. 5 sigma, 99.994% reliability, which literally means certainty. We call this the Higgs boson discovery standard. The K2-18b data is currently at the 3 sigma level, but scientists are aiming to reach the 5 sigma level in order to make a definite statement. Because the spread of such a discovery without being absolutely correct could lead to very big misunderstandings. To better understand this rate, the Higgs boson discovery standard, it means that if you make 1 million trials, you would only have a chance of being wrong 6 times. The most important feature that separates K2-18b from other planets is that it is probably a water world completely covered with oceans. These kinds of planets are called Hycean planets, worlds that host deep oceans beneath a thick, hydrogen-rich atmosphere. The absence of ammonia in the planet's atmosphere also supports this theory, because if there were giant oceans on the surface of the planet, ammonia would be dissolved in these waters. Think about it. Maybe we are talking about a planet whose oceans are 1,000 times larger and much deeper than ours, a world that could host much more life than the one we have. If the dimethyl sulfide on K2-18b is truly of biological origin, then the life there must be at an enormous scale. To be able to produce DMS at a concentration 1,000 times that of Earth, the biosphere of the planet has to be incredibly active. This situation brings up the following question. Could the oceans on K2-18b be hosting a diversity of life much richer than the most productive seas of Earth? Maybe a single drop of water there contains much more life than in our world? Behind this groundbreaking discovery is Professor Nikku Madhusudan and his team from the Institute of Astronomy at the University of Cambridge. While Madhusudan maintains his optimistic approach regarding the findings, other scientists are acting more cautiously. Experts like Dr. Nicholas Wogan from NASA Ames Research Center warn that K2-18b may not actually be an ocean world, but a mini gas giant. And now comes the most exciting part. According to Professor Madhusudan, within the next 1 to 2 years, it will be possible to confirm with 100% certainty the existence of dimethyl sulfide and prove its biological origin. After all these years of living completely alone in the universe, maybe we are experiencing the historic moment that in 2026 we will tell as the year we learned we were not alone in the universe. The additional observations to be made during this process and the confirmatory data to be obtained with different instruments may allow us to witness the greatest discovery in human history. Because if life on K2-18b is proven, this will not only say there is life in space, but also mean life may be much more common in the universe. The position of K2-18b is also thought-provoking. Although 124 light-years looks like an astronomical distance in human terms, on a universal scale it is actually considered right at our doorstep. On the map of the 93 billion light-year wide universe, this distance is really like finding something you were looking for in the back room of your house. Imagine that one day, the treasure you were searching for just came out of your basement while you were looking around. That's how close K2-18b is to us. This closeness actually points to a much deeper truth. If there is life at such a close distance, how many trillions of life forms might exist in the rest of the universe? This question brings the Fermi paradox back to the agenda. Where is everybody? The discovery of K2-18b also reveals how quickly technology is advancing. The fact that a planet discovered in 2015 could be analyzed in such detail in terms of signs of life just 10 years later shows how deeply science and technology are intertwined. This $10 billion project of the James Webb Telescope could prove that humanity is not alone in space. For me, this is the best way I have ever received the return of the taxes I paid. In the upcoming period, the studies to be carried out regarding K2-18b will not only confirm the presence of dimethyl sulfide, but will also produce a detailed atmospheric map of the planet. Scientists will be able to observe how the atmosphere changes during different seasonal cycles, if they exist, how the concentrations of gases fluctuate, and even daily changes. This data will help us understand not only whether there is life, but also what kinds of life forms might exist. For example, if the amounts of DMS in the atmosphere change in certain periods, this could indicate seasonal life cycles. But wait, what if I told you this is just the beginning? Imagine that today we're only scratching the surface, and the one real shock is still ahead, because the most mind-bending part is not just that K2-18b could host life, but what kind of life might be hiding there. And right at that moment when scientists thought they had everything figured out, another layer of mystery appeared. What if we are on the verge of finding not just microbes, but entire ecosystems thriving under alien oceans? Things were starting to make sense, until fresh data hinted that we might need to completely rewrite biology as we know it. Senol Sanleya, pardon, would you book the first ticket there, or would you rather stay safe on Earth? Don't miss this journey, hit like, subscribe, and share this video with anyone who's ever looked up at the stars and wondered. Because the real adventure is only just beginning. The story of a 10-year scientific adventure is the chronology of the search for an answer to humanity's greatest question. The discovery of K2-18b is a perfect example of how modern astronomy works, a magnificent symphony of patience, technology, and scientific collaboration. Behind this knowledge, which is still very new to us, lies the efforts of hundreds of scientists who worked tirelessly day and night for 10 years. March 9, 2015 was a special day in the history of space exploration. The Kepler Space Telescope, as part of its K2 second light mission, was scanning the depths of space, hunting for planets. At that time, scientists did not yet know how great a meaning this discovery would carry. The working principle of Kepler is fascinating. With this method called transit photometry, it detects tiny changes in light when planets pass in front of their stars. Imagine detecting a 0.01% change in the light of a star 124 light-years away. This is truly an incredible ratio. It is as difficult as noticing that just one bulb out of thousands used to light up a football stadium is not working. During the discovery of K2-18b, Kepler noticed small decreases in the star's light that repeated at regular intervals. These periodic decreases repeated every 33 days. The eureka moment. This indicated the presence of a planet regularly passing in front of the star. That the Kepler Space Telescope was able to make this discovery was a technically incredible achievement. The telescope was simultaneously monitoring about 150,000 stars per second. Detecting potential planets like K2-18b within this massive data flow was much harder than looking for a needle in a haystack. During the K2 mission at that time, more than 200 planets were discovered, but K2-18b drew the special attention of scientists because even the first data showed that this planet was in the habitable zone. So why did only K2-18b receive special interest among 200 planets? The reason was that K2-18b resembled Earth to a degree and in a way that had never been seen before in any other planet. 2 years later, the Spitzer Space Telescope entered the stage. Spitzer's mission was critical to independently verify Kepler's findings and gather more detailed information about the planet. In science, data from a single source is never enough. Cross-validation is one of the cornerstones of the scientific method. Spitzer's infrared observations definitively confirmed that K2-18b was indeed located in the habitable zone. This region is also called the Goldilocks zone. Not too hot, not too cold, just warm enough for water to exist in liquid form. At the same time, the HARP spectrograph at the La Silla Observatory in Chile was also brought into action. This highly sensitive instrument focused on determining the mass and density of K2-18b. Using the Doppler spectroscopy method, it measured the gravitational vibrations the planet created in its star. That HARPS was able to make these measurements was a technically great achievement. It detected that the K2-18 star was oscillating at a speed of 2.3 meters per second. This speed is slower than a human walking at a slow pace. This measurement was so precise that scientists had to work on it for years to be certain. Measuring that a star 124 light-years away was wobbling at a speed of 8 kilometers per hour, this was almost impossibly precise. As a result of these measurements, it was determined that K2-18b was 2.2 times larger than Earth and 8.6 times heavier. More importantly, when its density was calculated, it was understood that the planet most likely had a thick atmosphere. The year 2019 was a new turning point in K2-18b research. The Hubble Space Telescope, after long observations, detected water vapor in the planet's atmosphere. This discovery created great excitement in the scientific world because water is an indispensable component for the life forms we know. Hubble's discovery was made using the transit spectroscopy method. As the planet passed in front of its star, part of the starlight filtered through the planet's atmosphere. Different molecules in the atmosphere absorbed light at certain wavelengths, leaving their unique spectral signatures. That planet, 124 light-years away, was almost sending signals saying, "I am here." And when scientists noticed these mysterious messages, they dedicated themselves for 10 years to solving this mystery. And in the end, they succeeded. Detecting water vapor with Hubble was not easy. During an 18-month observation period, the planet's transit across its star was observed a total of 10 times. Each transit lasted about 3 hours, and during this time, it was necessary to collect enough data for spectral analysis. The biggest challenge was improving the signal-to-noise ratio. The spectral signature of water vapor was so weak that atmospheric turbulence, telescope vibrations, and even solar winds could affect the measurements. To overcome these problems, scientists had to use advanced algorithmic techniques. The year 2023 was when the real revolution in K2-18b research took place. The first observations made with the James Webb Space Telescope's NIRCam, near-infrared camera instrument, shocked the scientific world. Because what was detected in the atmosphere was not only water vapor, there were also traces of dimethyl sulfide, DMS. James Webb's advantage was that it was 100 times more sensitive than Hubble. This difference in sensitivity made faint, spectral lines visible that had never been detected before. The spectral signature of DMS was so weak that it could only be noticed with James Webb's advanced technology. As if, for humanity searching the skies for life, suddenly super-powerful eyes were given, like a captain scanning the horizon with binoculars, but this time the binoculars were turned toward the universe. Although the first detection of DMS created great excitement, scientists remained cautious. Because in the near-infrared bands where NIRCam operates, distinguishing dimethyl sulfide from methane gas was extremely difficult. The spectral lines were so close that they were at the very limits of the instrument's sensitivity. Dr. Niku Madhusudan and his team were aware of this situation, saying, "Relying on a single measurement is not scientific," they decided, to make additional observations with different instruments for independent verification. April 17, 2025 will go down as one of the most important days in the history of science. A second series of observations, this time using James Webb's MIRI, mid-infrared instrument, definitively confirmed the presence of DMS. This time, the wavelength range used was different, and there was no possibility of DMS being confused with methane. Two independent instruments giving the same result was considered the gold standard in science. Even more surprising was that the concentration of DMS turned out to be 1,000 times higher than Earth's levels. Faced with this number, scientists were shocked because it pointed to immense biological activity. Turning raw spectral data into meaningful results required months of complex analysis processes. Scientists processed the data using machine learning, algorithms and statistical modeling techniques. The most challenging part was eliminating false positives. Water vapor, carbon dioxide, and other gases in the atmosphere could sometimes create patterns similar to DMS signatures. Therefore, cross-correlation analyses and Monte Carlo simulations were performed to test the reliability of the results. In this universe, whose end we cannot fully comprehend, searching for life with a telescope was like trying to find a single molecule in an ocean. But we succeeded. This 10-year process of discovery is also the story of humanity's technological evolution. What began in 2015 as a signal as small as a pixel turned by 2025 into evidence that could answer the greatest question in the universe. Don't you feel proud to be a witness to this historic process? In the future, when you tell these moments to your children, you will be able to say that you followed the step-by-step developments as a part of living history. The most beautiful aspect of science is that it does not easily reach absolute truths. The scientific debates surrounding the possible discovery of life on K2-18b are a perfect example of how modern astronomy works. Like every major discovery, this one is shaped by the clash of skepticism and excitement. The discussions among scientists resemble the atmosphere when humanity first discovered the moons of Jupiter. Within the scientific community, there is a profound division of opinion about the nature of K2-18b. This division is not just an academic debate, it is a critical issue that fundamentally affects the possibility of life on the planet. The Cambridge University camp, led by Professor Niku Madhusudan, argues that K2-18b is a Heitsian-type ocean world. According to this theory, the planet harbors deep oceans beneath a thick hydrogen atmosphere. The presence of dimethyl sulfide in the atmosphere suggests that these oceans are biologically active. On the other hand, Dr. Nicholas Wogan from NASA Ames Research Center and his supporters believe that K2-18b is actually a mini-gas giant. According to this view, the planet has a Neptune-like structure and lacks a solid surface. Both sides have strong reasons for their interpretations of the data. What do you think about this? Do you believe there is truly life there? Or is it just clouds of giant gas? The density of K2-18b lies at the heart of this debate. The planet is 2.2 times larger than Earth, but 8.6 times more massive. Based on these measurements, its calculated density comes out to around 2.3 grams cm3t. This density value falls exactly within the zone of uncertainty. Earth's density is 5.5 g cm3, while Neptune's is 1.6 g cm3. K2-18b's 2.3 g cm3 places it in a range that could fit either planet type. Now think about what these numbers mean. If the planet has a largely rocky core, then its atmosphere would be relatively thin and oceans might be possible. However, if it is mostly composed of ice and gases, then there may be no solid surface at all. It's as if we are holding a heavy sphere and trying to figure out what makes it heavy, but the sphere is so far away that we cannot see inside. The uncertainty regarding K2-18b's surface temperature directly affects the possibility of life. The planet is located 2.3 AU from its star, 2.3 times the Mercury-Sun distance. But since its star is much cooler, the energy reaching the planet is similar to Earth's. However, greenhouse effect calculations complicate things. If the planet has a thick hydrogen atmosphere, this atmosphere could create an enormous greenhouse effect. According to Dr. Wogan's calculations, surface temperatures could exceed 100 degrees C, and in some regions even reach 200–250 degrees C. At such temperatures, life forms as we know them cannot survive. Proteins denature, DNA structures break down, and even water becomes supercritical, losing its normal properties. On K2-18b, such extreme heat may suggest not living organisms, but rather a hellish mix of boiling chemical remnants. The data on K2-18b's atmospheric composition also lead to conflicting interpretations. The gases detected by the James Webb Telescope are water vapor, H2O, definitely detected carbon dioxide, CO2, present in low concentrations, methane, CH4. Uncertain, may overlap with DMS dimethyl sulfide, DMS. The most controversial component, ammonia, NH3, not detected. This is an important clue. The absence of ammonia is particularly striking. If the planet truly harbors deep oceans, ammonia could have been absorbed by them. This supports Cambridge's ocean theory. However, skeptics offer a different explanation. The absence of ammonia could also result from the planet's high temperatures. At such levels, ammonia breaks down into nitrogen and hydrogen. In a place with so many components, scientists believe much more research is needed before conclusions can be made with certainty. All possibilities are laid on the table, examined, and eliminated one by one until the true scenario emerges. The biggest point of debate is the origin of DMS. On Earth, this gas is produced almost exclusively through biological processes, but could different mechanisms exist on other planets? Geothermal origin theory. Some scientists suggest that DMS could be produced as a result of volcanic activity. Sulfur compounds can also form through geological processes and then react with carbon compounds in the atmosphere to generate DMS photochemical processes. It is possible for DMS to form through the interaction of stellar radiation with simple molecules in the atmosphere. While these processes are not common in Earth's atmosphere, they could be more active under different atmospheric conditions. Abiotic chemical reactions. At the interface between a hydrogen-rich atmosphere and potential oceans, DMS could be produced through non-living chemical processes. We can imagine DMS as a criminal's fingerprint, but we have not yet discovered who left it, and we must also consider the possibility that multiple criminals could leave this same fingerprint. The statistical significance of the K2-18b findings is also a topic of discussion. Currently, the data stand at a 3 sigma confidence level, 99.7%, but they have not yet reached the 5 sigma level, 99.994%, which is the standard for scientific discovery. This difference may seem small, but it carries great importance in the scientific world. The jump from 3 sigma to 5 sigma represents moving from a 1 in 300 chance of error to a 3 in a million chance of error. The Higgs boson discovery was accepted at the 5 sigma standard. Gravitational wave detections also met this standard. For K2-18b's findings to reach this level, more observations and independent verification are required. The James Webb Telescope, being a new technology, raises concerns for some scientists. Even though the MIRI and NIRCam instruments are calibrated, the possibility of systematic errors is not completely eliminated. Spectral line overlap is particularly problematic. Because the spectral signature of DMS is so weak, it could be confused with the instrument's noise. Therefore, some experts recommend independent verification with other telescopes before the findings are considered definitive. The European Space Agency's Euclid telescope and the upcoming Roman Space Telescope could play a critical role in this verification process. There are 2 main reasons why this problem is difficult to resolve. First, DMS leaves an extremely weak spectral signature, and second, we cannot be entirely certain that the James Webb Telescope is performing measurements with perfect precision. Another factor complicating the scientific debate is media and public pressure. Headlines like life found in space attract huge attention, but they also create pressure on scientists to announce results quickly. Dr. Madhusudan's team is working to manage this pressure while adhering to the principles of scientific integrity. They adopt the approach, "We cannot say anything for certain yet, but the findings are very promising." Skeptical scientists, on the other hand, operate under the principle, "Extraordinary claims require extraordinary evidence." Carl Sagan's famous quote is frequently cited in discussions about K2-18b. The next 18 months will be critical for the fate of K2-18b. Additional observations from the James Webb Telescope, the involvement of the European Extremely Large Telescope, ELT, and contributions from other next-generation instruments are expected to resolve most of the scientific uncertainties. Which view will ultimately prevail, do you think? The ocean world theory or the mini-gas giant hypothesis? In any case, the fact that incredible knowledge is being passed to future generations remains unchanged, and it will very likely, and perhaps certainly, make a significant contribution to the advancement of science. This scientific uncertainty actually demonstrates the power of science. While reaching definitive conclusions takes time, this process is precisely humanity's effort to answer the deepest questions about our place in the universe. And we are right in the middle of this historic process. Get ready for a journey that will push the limits of your imagination. If life really exists on K2-18b, these creatures will probably resemble nothing we have seen on Earth. On this mysterious world, 124 light-years away, evolutionary processes may have followed completely different paths. This endless chain of possibilities further entices our curiosity and drives us to pursue the truth like crazy. The possibility of not being alone in space, the chance to discover a different civilization, both excites us and scares us a little, but the most shocking part is still ahead. Imagine discovering a world where every rule of life you know suddenly collapses. Would you dare to keep watching? Because what comes next will change the way you think about alien life forever. Every story requires a beginning, and the story of life on K2-18b probably starts with microorganisms. As on Earth, the first forms of life are most likely to be microscopic. However, these microorganisms may resemble no microbe on Earth. Microorganisms that could live under K2-18b's thick hydrogen atmosphere would likely possess extremophile, resistant to extreme conditions, traits. Microorganisms living near hydrothermal vents at the bottom of Earth's deep oceans could serve as a good reference point for K2-18b life. And just at that moment, a question strikes: what if these creatures are not just surviving, but building civilizations deep in their oceans? What if they've already mastered technologies we can't even imagine? Microbes living on this distant world could survive through chemosynthesis, chemical energy conversion. Hydrogen sulfide, methane, and other organic compounds in the hydrogen atmosphere could provide a rich energy source for them. However, we must not overlook that gases considered toxic on our world may be the most fundamental source of life for them, just as oxygen is a fundamental component for us. One of the most striking features of K2-18b is its hydrogen-rich atmosphere. This could allow radically different metabolic processes to evolve from Earth life. Can you imagine organisms breathing hydrogen instead of oxygen? These creatures may have perfected anaerobic respiration, meaning oxygen-free respiratory processes. They could produce energy by breaking down hydrogen molecules, producing water and simple carbohydrates as waste products. This process would function as a mechanism opposite to photosynthesis on Earth. Now close your eyes and imagine creatures that have evolved for billions of years in a hydrogen atmosphere may have silver metallic cell membranes. These membranes could contain special proteins that work more efficiently in a dense hydrogen environment. Just like in science fiction movies, their skin could be covered with crystals that reflect or bend light. organisms that don't exist on our world but for them act as natural prisms. K2-18b's low-density hydrogen atmosphere and probable deep oceans could provide ideal conditions for the evolution of giant marine creatures. The high buoyancy of hydrogen air allows large creatures to move more easily. These giant creatures could have jellyfish-like structures, semi-transparent, gel-like bodies. But much larger than Earth jellyfish, their diameters could range between 50 to 100 meters. These massive beings could drift slowly in the mid-layers of the ocean, feeding on plankton-like small organisms. Thanks to the buoyancy advantage, some creatures could develop a semi-atmospheric lifestyle. Organisms living near the ocean's surface could keep part of their bodies underwater and part in the hydrogen atmosphere. That is, these creatures could live both in water and on land. The deep oceans of K2-18b are probably completely dark. Starlight is largely absorbed as it passes through the thick atmosphere and water layers. Under these conditions, bioluminescence, living light production, becomes a critical adaptation. On Earth, bioluminescent organisms produce light using molecules called luciferin. K2-18b's creatures may have developed more efficient light production mechanisms. In a hydrogen-rich environment, hydrogen peroxide-based light systems could be more common. The light production of these creatures may not only serve for vision, it could be used for communication, hunting, and even defense. Imagine, in the dark depths of the ocean, giant creatures putting on colorful light shows, exchanging complex messages with each other. Have you ever thought that their communication could be through light, unlike our voice and visual communication? Imagine, when we go there, we would see thousands of dancing lights in the sky or among them while they converse, knowing that this is their source of communication. Can you imagine seeing red and spiky lights when they are angry, blue when sad, and wildly spreading colorful lights? How would it really feel to experience something like that? Would you want to live it? The oceans of K2-18b could be much deeper than Earth's oceans. At depths of 15-20 kilometers, the pressure could reach 2,000-3,000 atmospheres. Creatures capable of surviving these extreme conditions must have developed tremendous pressure adaptations. These pressure giants likely have thick, flexible exoskeleton structures, like the exoskeletons of crabs and shrimp on Earth, but much stronger and more flexible. These protective systems, made of biopolymer-based materials, are both pressure-resistant and allow mobility. The internal structure of their bodies may also contain special adaptations. They could be equipped with compression-resistant organs, pressure-balancing channels, and specialized circulatory systems. This could give them the ultimate capability to live in the deepest parts of their oceans. It would probably be much harder for us to explore as we struggle even with the depths of our own oceans. However, the mere possibility of this is quite promising for us. K2-18b's mineral-rich ocean could allow the evolution of life forms containing metallic components. These creatures could concentrate iron, nickel, and other metals in their bodies to create ultra-durable biological structures. Metalloproteins, metal-containing proteins, could be much more common in these creatures. While hemoglobin contains only iron, K2-18b's organisms could have developed complex proteins containing multiple metals. This could provide them with superior oxygen-carrying capacity, or hydrogen carrying, on K2-18b. Some creatures might even have become natural electrical conductors. The metal concentration in their bodies could be so high that they surpass Earth creatures in bioelectric production and conduction. Imagine creatures capable of producing multiple times more electricity than our electric eel roaming around like living batteries. This dream may not be impossible. K2-18b's thick hydrogen atmosphere could also allow fully atmospheric life forms to evolve. These creatures never descend to the ocean, spending their entire lives in different layers of the atmosphere. These atmospheric creatures likely have balloon-like structures. By storing low-density gases inside, they can keep themselves afloat. They could be a much more advanced version of the microbial life proposed to exist in Venus's atmosphere. For nutrition, they could rely on aeroplankton, small airborne organisms, or chemical filtration methods. They could generate energy by exploiting chemical gradients in different layers of the atmosphere. Symbiotic life forms, co-living organisms, could be very common on K2-18b. Organisms with different metabolic processes could merge to form superorganisms. One species could process hydrogen, another carbon dioxide, and a third sulfur compounds. These highly diverse organisms would resemble nothing we have seen on Earth. They could form stationary structures like coral reefs, but each coral could actually be the result of dozens of species working together. They could also enable the development of collective intelligence. Thousands of small organisms could come together to form a single decision-making mechanism. A similar example exists in fungi on our planet. Small units form colonies, making decisions based on task distribution. One part of the colony handles nutrition, another waste, and a few other functions like respiration. By combining, they create a giant brain, increasing their chances of survival. Perhaps such creatures exist 124 light-years away. Who knows? K2-18b's 33-day orbital period and probable tidal locking could seriously affect these creatures' perception of time. Living in an environment without a day-night cycle, they may have developed completely different biological rhythms. These creatures may have much longer life cycles. Processes that Earth organisms complete in days could take months, or conversely, with hyperfast metabolism, they could complete their life processes in seconds. Now pause for a second. If you were standing there in front of a glowing ocean, filled with metallic giants and living lights, what would you do? Would you run, explore, or simply stare in awe? Tell me in the comments. I'd love to know. If life truly exists on K2-18b, we will witness the unlimited power of evolutionary creativity. These creatures could rewrite the fundamental rules of Earth life and radically change our understanding of biology. The possibilities are so vast that humans cannot help but marvel. Intelligent beings may exist in their own universe, 124 light-years away, wondering if they are alone, just as we investigate the possibility of their existence. Science, space, and technology are truly incredible tools, holding unimaginable surprises. I am very happy to have researched this topic, learned what I could, and shared it with you. I hope you enjoy the video, and if so, I would appreciate a like in advance. Thank you. Which life form interests you the most? The giant jellyfish or the metallic creatures? Think about which life form you would describe most excitedly when telling this story to your children. What does this universe full of infinite possibilities mean for us? Perhaps we will learn that life is far more strange and resilient than we could ever imagine. In the depths of the universe, there are exotic planets that challenge scientists' imaginations and test the limits of physical laws. These strange worlds show how extraordinarily life could develop under conditions far beyond those on Earth. This truly means that in an infinite universe, there could be infinite possibilities for life. Consider the planet J147b. This world makes Saturn look like a toy. This giant ringed planet, 434 light-years away, has 10 to 40 times the mass of Jupiter. But what's truly astonishing is its ring system. It has 30 rings extending millions of kilometers in diameter, reaching a total span of 120 million kilometers, exactly 200 times larger than Saturn's rings. I think we've really found Saturn's father. If J1407b's rings were in our solar system, they would dominate our night sky. Just like the moon, we could see J1407b in the sky, perhaps even larger than the moon. Imagine if one day you looked up and saw such a view, how would you react? However, this visual feast wouldn't last forever, because over time the rings thin out and form moons around the planet. GJ504b, on the other hand, is the champion of color. This pink planet is 57 light-years away and has 4 times Jupiter's mass. So where does this exotic color come from? The answer lies in the planet's youth. This newborn world, only 160 million years old, is still losing the heat it gained during formation, giving it a matte magenta glow. The water-dominated GJ214b tells a completely different story. This water world has more than 8 times the mass of Earth and a radius 0.24 times that of Jupiter. But the water on this planet is very different from what we know. At 200 TDA and under extreme pressure, it exists as a supercritical fluid, not quite liquid, not quite gas, a mysterious state with properties of both. Imagine what it would feel like to swim in such water. Now get ready, we're heading to a real hell. Welcome to the Hell Planet, Kepler 70b. This scorching world has only 0.44 the mass of Earth and 0.75 its radius, yet its temperature reaches 6,600 Sun, higher than the Sun's surface temperature of 5,500 degrees. Located just 165 the distance of Mercury from the Sun, this planet is literally a world heated by the Sun. I guess it's not a suitable place for us to live. But could an intelligent species that withstands extreme heat have evolved there? WASP-76b, meanwhile, is an absolute meteorological nightmare. A planet where iron rains down as if from the sky, with molten metal waterfalls flowing magnificently. Located 640 light-years away and almost as large as Jupiter, this tidally locked world always shows the same face to its star. The daytime side reaches 2,150 degrees C, while the night side is almost twice as cold. This extreme temperature difference creates violent winds, vaporizing iron and mixing it into the atmosphere. The iron vapor transported to the cold side condenses and falls as molten iron rain. We have no idea what this would look or feel like, but we're sure umbrellas wouldn't help. PSR J1719 1430b is a true diamond planet story. This exotic world is 3,000 times larger than its neutron star. Of course, this is normal since the neutron star is only 20 kilometers in diameter. What's really interesting is that this planet used to be a star. Its outer layers were stripped away by the gravitational influence of a larger pulsar, and the remaining carbon crystallized into diamond. With a diameter of about 60,000 kilometers, this world is literally a giant diamond floating in space. At least for anyone who has ever imagined a room full of diamonds even once, living on this planet could feel perfectly normal. Imagine being able to take a piece of diamond from there. What would you do with it on Earth? Our lightest champion, WASP-107b, is a planet with the density of cotton candy. Jupiter-sized, but only 30 times the mass of Earth. Considering Jupiter has 300 Earth masses, this really is like a marshmallow floating in space. Its core is only 4 times the size of Earth's, whereas it should have been 10 times larger. This extremely low density is causing scientists to reconsider their theories about how gas giants form. The promising Gliese 581d stands out as a potential colonization target. Could this be our new home? Located just 20 light-years away, this habitable planet has 6 times the mass of Earth and lies within its star's habitable zone. Even though it may be tidally locked, its atmosphere, rich in carbon dioxide, prevents the night side from freezing. Living in the twilight zone, the boundary between day and night, might be possible. Mass J2126, with the longest orbit, tells a story of a truly lonely planet. This world is 1 trillion kilometers away from its star, 7,000 times the Earth's sun. Distance: a year on this planet equals 900,000 Earth years, so if you lived there, celebrating your birthday would be impossible. If you were born there, you'd be like butterflies, born and dying on the same day. Life for us there could last only a few hours. Just the possibility of this is amazing. Exomoon discoveries are also exciting. Around the planet, PDS 70c, a disk forming moons has been detected for the first time. This disk contains enough material to form 3 moons, each the size of the moon. For the first time in human history, we are witnessing the birth of moons live. If you were there to witness a moon's birth, what would you name it? The KOI 5AB system is part of a triple star system. This planet, half the size of Saturn, initially seemed like science fiction because it is so complex. Orbiting star A, the planet, and its nearby companion, star B, orbit each other every 30 years. The third star, C, orbits both every 400 years. If you lived in this system, you would see 2 suns in the sky, one 17 times brighter than our sun, the other half as bright, but still 1,000 times brighter than the full moon. Seeing 2 suns in the sky would be truly fascinating. Would it make the weather hot? You can't help but wonder. Theoretical black hole planets go beyond science fiction. These exotic worlds could form from gas and dust collisions around supermassive black holes with orbits lasting millions of years. They would be some of the strangest worlds imaginable in the universe. The universe is limitless not only in distance, but also in creativity. Do you think our imagination is enough? Yet these beauties that surpass our imagination will certainly expand us and our way of thinking. Among the 5,000 exoplanets discovered so far, these are just the beginning. Who knows what else is waiting to be discovered? These strange worlds show how life could exist under vastly different conditions and might even signal that our solitude in the universe is coming to an end. K2-18b is not alone. In the depths of the universe, dozens of planets that give hope for life silently orbit their stars. These cosmic neighbors are each filled with unique stories and possibilities. The truth is, perhaps at the very moment you are reading these lines, a being similar to you on one of these planets is watching space with the same curiosity. It's as if we live in a giant neighborhood trying to find each other, and every home contains a different life story. When will we exactly discover our neighbor? Teegarden B, only 12.5 light-years away, can be considered almost a next-door neighbor on a cosmic scale. This distance is so close that if we could travel at the speed of light, we could reach it in roughly the duration of a university education. Estimated to have a 60% chance of Earth-like conditions, this planet is one of the most intriguing worlds for scientists. The most remarkable feature of Teegarden B is its perfect temperature range. Temperatures between 0°C and 50°C provide an ideal environment where both liquid water and organic molecules can remain stable. Imagine what could be possible within this temperature range. Life diversity extending from polar regions to tropical climates. However, Teegarden B's greatest challenge is tidal locking. One side of the planet constantly faces its star, while the other remains in eternal darkness. This creates extreme temperature differences, one side scorching hot, the other freezing cold. This is where the terminator zone comes into play. This narrow strip between the day and night hemispheres experiences perpetual twilight. It is neither too hot nor too cold, potentially providing ideal conditions for life. We predict constant wind currents in this twilight zone. Air moving from the hot side toward the cold side creates dynamic weather conditions in this region. These winds could mix atmospheric chemicals, creating rich chemical cycles. Use your imagination. Creatures living in this zone may have continuously adapted to the twilight. large eyes, advanced hearing, and possibly infrared vision. Like our vampire stories, but this time referring to real vampires. Of course, we will discover whether their blood is red like ours. Kepler 1649c, 301 light-years, away silently shines in the Cygnus constellation. While this distance seems enormous by human standards, it is still relatively close on a galactic scale. The most striking feature of Kepler 1649c is its astonishing similarities to Earth. The planet is only 6% larger and 20% heavier than Earth. This means the gravitational force will be almost identical to Earth's. Walking on Kepler 1649c would not be very different from walking on Earth. However, there is the light issue. The planet receives only 25% of the light Earth receives from the Sun. This suggests the planet could be quite cold. But if a greenhouse effect occurs, the situation could change. A thick atmosphere could keep the surface temperature at habitable levels. Kepler 1649c's star is a red dwarf, much smaller, cooler than the Sun. These stars have an incredible advantage. They can continue producing energy for trillions of years. While the Sun will stop burning in 5 billion years, red dwarfs will continue shining until the end of the universe. This means that if life exists on Kepler 1649c, it has an incredibly long time to develop. Life on Earth reached its current level in 4 billion years. Imagine the level Kepler 1649c's creatures could reach in 100 times longer. Perhaps they are already far beyond what we can imagine, while we are still like a baby in the crawling stage for them. Toei 700, 101 light-years away, holds a special place among habitable planet candidates. Unlike other candidates, it probably does not experience tidal locking, meaning it has a day-night cycle. This provides a tremendous advantage. Day-night cycles are critical for the development of biological rhythms. Almost all life on Earth has developed circadian rhythms, 24-hour cycles. Similar evolutionary pressures may be at work on TOI 700d. The planet receives 86% of the light Earth gets from the Sun. This means a slightly cold but habitable environment. Its surface temperature is estimated to be around 4 degrees C. Though cold, this temperature could easily be increased by the greenhouse effect. TOI 700d's star, TOI 700, is exceptionally calm for a red dwarf. Most red dwarfs produce powerful solar storms and X-ray flares. This radiation bombardment can strip away planetary atmospheres, but TOI 700 is different. It shows minimal solar activity. This means the planet could maintain its atmosphere for billions of years. A stable atmosphere, long-term chances for life. Just like our protected world, this is a great prospect both for natural disasters and for life chances and diversity similar to those on Earth. Proxima Centauri, B424 light-years away, is our closest exoplanet neighbor. This distance is so close that future robotic probe missions are being considered. Microscopic spacecraft like the Breakthrough Starshot project could reach it in 20 years at 20% of light speed. The habitability of Proxima b is debatable. Its star, Proxima Centauri, is a very active red dwarf, frequently producing strong solar storms. These storms could severely damage the planet's atmosphere. However, the situation could be different for underground life. Microorganisms living beneath the surface could be protected from surface radiation. Perhaps life on Proxima b hides in the depths. Assuming life exists only on the surface would be extremely shallow. The organisms there could have unique underground worlds. There could be truly unique life, civilizations, even cultures in places we cannot see or reach. I really love these endless possibilities in space. Ross 128b, 11 light-years away, offers a very stable system. Its star, Ross 128, is an extremely calm red dwarf. Solar storms are almost non-existent, making it ideal for atmospheric protection. Ross 128b is 1.35 times larger than Earth and probably rocky. Its temperature is estimated to range between 60 degrees Celsius and 120 degrees Celsius. This range could support polar life forms. An interesting detail: the Ross 128 system is moving toward our solar system. In 79,000 years, it will become the closest star system. Our cosmic neighbor is slowly approaching our door. How will we welcome it? Will this happen in our lifetime, or will future generations witness it? LHS 1140b, 40 light-years away, is one of the most promising candidates in the super-Earth category. It is 1.7 times larger and 6.6 times heavier than Earth. This size provides a strong magnetic field and the capacity to retain a thick atmosphere. The planet's density classifies it as a rocky world. Its surface temperature is estimated around 7 degrees Celsius, icy but habitable. Organisms with antifreeze proteins could live here comfortably. Wolf 1061c, 14 light-years away, is located at the very edge of the habitable zone. This makes it a borderline case, perhaps habitable, perhaps too hot. The planet is 4.3 times heavier than Earth and probably in the super-Earth category. If it has a thick atmosphere, the greenhouse effect could make it very hot. But if its atmosphere is thin, it could have perfect temperatures. Kepler 442b, 100 light-years away, is distant but very promising. It is 1.34 times larger than Earth and lies at the optimal point of the habitable zone. This planet has a 665-day orbital period, meaning 1 year is almost equivalent to 2 of our years. Long seasons may occur, allowing life to develop different evolutionary strategies. The James Webb Space Telescope will examine many of these planets in detail in the coming years. Water vapor, oxygen, methane, and other biosignatures will be sought. Each observation could provide new clues in our search for life. Which planet do you think is the most promising? The nearby neighbor Teegarden b or the stable Ross 128b? If you could travel with your cosmic vehicle, which would you go to? This collection of planets shows us the universe may be full of life, we just need to look in the right places. And perhaps one of these cosmic neighbors is currently waiting for news from us. Multiple star systems present one of the most fascinating scenes in the universe. For those of us accustomed to our single star, the Sun, systems where 2, 3, or even 4 stars dance together simultaneously seem almost like science fiction. But the truth is, more than 60% of stars in the universe reside in multiple systems. This means that lonely stars like ours are in the minority. We might actually be living in what the universe would call an anomaly. Are we an anomaly for the universe? The KOI 5AB system is one of the most interesting examples of this. This planet, half the size of Saturn, initially appeared so complex that scientists considered it science fiction. Truly, something we are not used to can seem like a product of imagination. We struggle to accept the possibility, the reality of such things. But these imagined things are actually happening. A decade later, upon re-examination, it was confirmed to be part of a triple star system. In this system, a planet orbiting star A dances around its close companion, star B, once every 30 years. The third member, star C, orbits this pair every 400 years. Imagine living on such a world. You would see 2 suns in the sky. What would a planet with 2 suns be like? Would plants photosynthesize more, or would the heat make them wither? The first sun is 17 times the size of our sun, while the second is only 0.5% as bright, but still 1,000 times brighter than a full moon. Binary star systems are the most common star configuration in our galaxy. The Sirius system is the most famous example. Bright Sirius A and its companion white dwarf Sirius B have been orbiting each other for millions of years. This perfect cosmic waltz over millions of years truly deserves our attention. Planet formation in such systems is quite challenging because gravitational interactions constantly redistribute material. The Alpha Centauri system holds a special place as the closest multiple star system to us. Alpha Centauri A and B orbit each other at an average distance of 23 AU, about the distance of Uranus from the Sun. Proxima Centauri is the third member, 13,000 AU away, orbiting them. The discovery of the planet Proxima Centauri b added a new dimension to the search for habitable worlds in multiple systems. Kepler 16b became famous as a Tatooine-like world. The planet from Star Wars where Luke Skywalker lived became real. This planet orbits the common center of mass of two stars, truly a two-sun world. With surface temperatures ranging from 70 degrees C to 100 degrees C, this icy world proved that planet formation is possible in multiple systems. HD 188753 Ab was the first hot Jupiter discovered in a triple star system. This giant planet, orbiting very close to its primary star, follows a chaotic orbit under the gravitational influence of the other two stars. What would seasons be like on a planet constantly exposed to the influence of three suns? This system helps us understand how multiple stars affect planetary dynamics. The Castor system is a true stellar collection. Castor, which appears as a single star to the naked eye, is actually composed of 6 stars. 3 pairs of binary stars perform a complex dance around each other. This system demonstrates how intricate star formation processes can be. The harmonious dance of these 3 pairs shows how masterful the universe is. Everything flows naturally and perfectly in sync. P-type and S-type orbits are critical concepts for planets in multiple systems. In a P-type orbit, the planet surrounds all the stars like Kepler 16b, while in an S-type orbit, it orbits just one star, like planets in the Alpha Centauri system. In both cases, achieving gravitational stability is extremely challenging. The Algol system is the prototype of eclipsing binary stars. Every 2 days and 20 hours, the dimmer star passes in front of the brighter one, reducing the system's brightness. By 70%, this cosmic wink was called the Eye of the Devil by ancient astronomers. I don't know how ancient people felt about this wink, but our early ancestors developed superstitions based on it. Black hole planets, the ultimate frontier. Black hole planets. Just saying those words out loud can send a chill down your spine. Could worlds really form around black holes, the most terrifying and mysterious objects in the universe? It's a question that doesn't just stretch physics. It rips open the imagination of both scientists and storytellers. And here's the twist. Cutting-edge simulations suggest these bizarre worlds might not just be possible. They could already exist, but the shocking part is yet to come. Supermassive black holes dominate the centers of galaxies, devouring matter. With billions of times the Sun's mass, galactic titans like Sagittarius A carve out enormous accretion disks, swirling with dust and gas. Over millions of years, collisions within these disks could actually forge planetary seeds. Yes, you heard that right. The heart of our galaxy might already be incubating hidden planets. And if planets can really grow up in such hostile cradles, we must ask, could life begin there too? Where time breaks, gravitational time dilation is perhaps the most mind-bending feature of these black hole planets. According to Einstein's relativity, the closer you get to a black hole, the slower time flows. Imagine stepping onto the surface of such a planet. One day, for you, could mean centuries passing across distant galaxies. Think about it. If you left your loved ones for what felt like 24 hours, you might return to find them long gone or older than you could ever imagine. Knowing this, Would you still take that trip? We've seen a glimpse of this in cinema. Remember Miller's planet in Interstellar? That was fiction, but the physics is real, and yet the real shock is still waiting. The birthplace of worlds' accretion disks aren't just cosmic graveyards, they're also nurseries. Matter spiraling into the black hole heats up to millions of degrees, blasting X-rays into space. But in the outer regions, far from the fiery core, temperatures drop to a few hundred Kelvin, perfect conditions for planet formation. Here, magnetohydrodynamic turbulence can help dust grains stick together, clumping into planetary embryos. Step by step, kilometer by kilometer, rocky worlds might coalesce in the most unexpected place of all. Just when it looked impossible, life finds a loophole. Safe zones in the shadows planets can't survive everywhere near a black hole. Venture. Too close and you're doomed. But beyond the Schwarzschild radius, and especially outside the ISCO, innermost stable circular orbit, orbits can remain stable for billions of years. Around rotating Kerr black holes, thanks to frame dragging, these safe zones could be even tighter. What would the seasons look like on such a world? Would years last centuries or minutes? Could sunsets stretch on forever? And just when you think you've grasped it, something else happens. The cosmic race. Against evaporation, Hawking radiation, slowly bleeding energy from black holes, is usually negligible for giants. Stellar mass black holes evaporate on timescales longer than the age of the universe. But for primordial black holes, tiny relics of the Big Bang, the clock ticks fast. If planets form quickly enough, they could survive. But if not, they vanish in the blink of an eye. Which side wins? It's literally a cosmic race against time itself. Torn apart or born anew, the closer a planet drifts to its black hole parent, the more vicious the tidal forces become. Inside the Roche limit, planets are ripped apart, shredded into glittering rings. Metal-rich worlds with iron cores may resist longer, but icy planets? They unravel instantly, stretched into spaghetti by the black hole's gravity. And then you wonder, would your world survive, or would it be devoured? The chaos of binary. Black holes. Now imagine two black holes locked in orbit. Double the mass, double the chaos. Could Tatooine-like planets really circle such a deadly duo? Some researchers think so, and here's the cliffhanger. What if those black holes one day decide to merge? LIGO already detects the aftershocks of such cosmic collisions, tsunamis of energy powerful enough to ripple space-time itself. If your planet was caught in that moment, what would happen? Would you be hurled into interstellar space? Or would you vanish in less than a second, snuffed out before you even noticed? You tell me, what would you do? Quasars, planet factories, quasars blazing with the energy of active galactic nuclei may be the most fertile environments of all. Their accretion disks stretch across parsecs. In such megadisks, planets could form the size of entire solar systems. Take 3C273, one of the brightest quasars. It could host thousands of planets circling its inferno. Imagine looking up from one of those worlds, the sky ablaze with auroras powered by plasma jets, and still thinking, this is home. Auroras of fire and light protection is key. Without a strong magnetic field, black hole planets would be sterilized by radiation. But with one, spectacular things happen. Plasma storms and relativistic jets spark auroras so immense they would outshine anything on Earth. Would you risk your life just to witness such a sky? Energy from the abyss, rotating black holes have ergospheres, zones where energy can be stolen through the Penrose process. Planets tapping into this energy could experience internal heating, volcanic eruptions, even oceans of liquid water. In other words, black hole planets might not just survive, they could thrive. A hall of mirrors. Look up from the surface of one of these planets and you might see something impossible. Gravitational lensing twists light into Einstein rings, creates duplicate suns and warps the sky into surreal visions. Near the photon sphere, you could even glimpse your own back as light curves around the horizon. Good luck playing hide and seek there. The colors of time, redshift and blueshift, would paint the sky in constant change. Light from the black hole shifts crimson, while distant galaxies burn blue. A never-ending cosmic rainbow overhead, both terrifying and beautiful. The edge of physics, near these worlds the Hawking-Unruh effect, would trigger quantum fluctuations, vacuum polarization, virtual particles, Casimir forces, phenomena we barely understand, would shape everyday life. But then comes the strangest thought. What if cosmic censorship fails, exposing a naked singularity? Space-time itself could twist into closed, time-like curves, actual pathways through time. If you had the choice, would you leap forward to the future or revisit the past? Dark matter, dark energy, and wormholes. Black holes may also concentrate dark matter and dark energy in ways we don't yet comprehend. WIMP particles, axion fields, exotic chemistry. Planetary cores could be built from materials unknown to Earth. And then comes the wildest idea: wormholes. Planets orbiting near Einstein-Rosen bridges might act as cosmic airports, hubs for intergalactic travel. Would you make a stop over there, or would you choose a safer destination? Life on the edge. Astrobiologists speculate, could life survive on these planets? Extremophiles already thrive in radiation and crushing pressure here on Earth. On a black hole planet, life could be silicon-based, plasma-based, or something even stranger, perhaps feeding directly on MC2. Think about it. Entire ecosystems powered not by sunlight, but by space-time itself. The tools of tomorrow we might not have to imagine forever. Future telescopes like Next Generation, very long baseline interferometers, could detect planetary shadows orbiting black holes. Lensing surveys and precise astrometry could confirm their presence indirectly. Every year, we step closer to proof. The final frontier of life. Black hole planets are not just exotic curiosities, they are laboratories testing the boundaries of physics. If planets can exist even here, in the deadliest realms of the cosmos, doesn't that mean life might be far more resilient than we ever dreamed? Perhaps these worlds represent the final outposts of complexity, the last sparks of life before. The universe reaches heat death, and entropy claims everything. So here's the ultimate question. Would you live on a black hole planet? Tell me in the comments below. Smash that like button, subscribe, and turn on notifications, because this journey to the most extreme frontiers of the universe is only just beginning. And trust me, the best part is still to come. Exomoon discoveries have become one of the most exciting fields in astronomy. While our solar system has 79 moons orbiting Jupiter, why were the moons of exoplanets discovered so late? The answer lies in technical challenges. Detecting an exomoon is 1,000 times harder than discovering a planet. It's like finding a ring you dropped into the ocean. The PDS-70C system marked a groundbreaking discovery in this area. Thanks to the ALMA telescope in Chile, scientists detected for the first time a moon-forming disk. Humanity had never encountered anything like this before, and it was a huge surprise. This disk contains enough material to form 3 moons the size of our moon. Imagine, this is what our solar system looked like billions of years ago, and now we are witnessing it live. Why are exomoon studies so important? Because moons can provide critical conditions for life. The icy oceans on Jupiter's moons Europa, and Enceladus show that moons can have life potential. Thousands of organisms could currently be swimming quietly in these deep oceans. So what surprises might the moons in other systems hold? Exomoon. Hunting began with the transit photometry method. When a planet passes in front of its star, if it has a moon, additional fluctuations appear in the light curve. These mini-shadows need to be large enough for our telescopes to detect, meaning we have to look for moons at least the size of our moon. The first exomoon candidate, Kepler 1625b, caused great excitement among astronomers in 2018. This giant moon, 8,000 light-years away, is Neptune-sized and orbits a Jupiter-sized planet. However, this discovery still awaits confirmation. There's a chance of a false positive. The data analysis is so sensitive that even atmospheric turbulence can affect the results. Kepler 1708b. I went down in history as the second major exomoon candidate. This mysterious moon orbits much farther from its planet, and its size ratio is astonishing. The mass ratio between the planet and moon is even more extreme than the Earth-Moon system. This forces us to completely rethink moon formation theories. The combined power of the Hubble Space Telescope and the James Webb Space Telescope is revolutionizing the hunt for exomoons. This duo is starting a profound revolution in space and is practically overturning what we know. Webb's infrared sensitivity allows the detection of moons' thermal emissions. This gives hope even for cold moons because tidal heating can generate internal energy. The problem of dynamic stability is also critical. For an exomoon to remain stable around its planet for millions of years, it must stay within the Hill sphere. This gravitationally safe zone depends on the planet's mass and its distance from the star. Moons that are too close fall onto the planet, and those too far are pulled away by the star. Living in this cosmic balance, which resembles a survival game, wouldn't be very easy for you either, right? Tidal forces also play a decisive role in exomoon formation. The planet not only stretches and squeezes its moon, but also provides internal heating. This tidal heating allows liquid water to form even in distant systems where sunlight cannot reach. Europa's icy oceans are a perfect example. Io's volcanic activity is entirely powered by tidal energy. This energy is so strong that sulfur plumes erupt up to 500 kilometers high. Magnetosphere protection is also vital. The planet protects its moons from harmful radiation with a strong magnetic field. The differing geological activities of moons like Io, Europa, and Ganymede within Jupiter's radiation belts show how critical this protection is for life. Could there be living organisms on a planet specialized with a magnetosphere? Even Europa's thin atmosphere can be preserved thanks to this magnetic protection. Multiple moon systems are opening new horizons in exomoon research. If groups of exomoons orbiting in resonance chains like Jupiter's 4 large moons are detected, we can gain unique insights into the system's dynamics. The dance of the Galilean moons is a magnificent example of orbital harmony maintained over billions of years. The 4-2-1 resonance of Io, Europa, and Ganymede is the most beautiful composition of gravitational music. Thanks to spectroscopic analyses, exomoon atmospheres can be studied. Transit spectroscopy allows us to determine a moon's atmospheric composition. If signs of water vapor, carbon dioxide, oxygen, or other biosignatures are found, this could indicate biological activity. Complex chemical processes like Titan's methane cycle are possible on exomoons as well. Could the tangled signals from this distant moon provide the clearest signs of life? Artificial intelligence and machine learning are revolutionizing exomoon detection. Neural network algorithms can detect subtle changes in telescope data far faster than humans. Deep learning models analyze thousands of light curves in seconds to identify moon candidates. This technology will make the discovery of thousands of exomoons possible in the future. How will future technologies change exomoon discoveries? Many more secrets and great mysteries will be revealed with the telescopes of the future. Doesn't that excite you? Giant telescopes like the Extremely Large Telescope, ELT, and the Nancy Grace Roman Space Telescope will be able to detect moons even the size of Earth. Direct imaging may become possible with coronagraph technology. From an astrobiological perspective, why are exomoons so important? Because moon diversity increases the diversity of life forms. Moons at different distances experience different conditions. Close moons are warmer, distant ones colder, but tidal heating can keep them active. This environmental gradient is perfect for evolutionary diversity. Citizen science projects also play a role in exomoon hunting. Projects like Planet Hunters and LightCurve allow volunteers around the world to analyze telescope data. Perhaps the next exomoon will be discovered on your computer. Statistical predictions are also promising. The fact that our solar system has more moons than planets suggests there are trillions of exomoons in our galaxy. How many of these trillions of moons might harbor life? This number gives us endless possibilities in the search for habitable worlds. Exomoon discoveries not only reveal new worlds, but also help us understand the evolution of planetary systems. Moon formation processes can unlock the secrets of the early solar system and provide new clues about the origins of life. This cosmic, detective work could redefine humanity's place in the universe. Could our position in the cosmos be just an illusion? The reality might be far different. Can you imagine how vast our home universe is and exactly where we fit within it? Could the discovery of dimethyl sulfide on K2-18b answer humanity's greatest question? Detected 194 light-years away with 99.7% confidence, these potential biosignatures might signal the end of our solitude in the universe. But to grasp the significance of this discovery, we need to view it from a cosmic perspective. How will this discovery change the way we see life? The Drake equation is back in focus. Formulated in 1961 by Frank Drake, this mathematical estimate calculates how many communicative civilizations might exist in our galaxy. The K2-18b discovery dramatically increases the parameter for planets capable of supporting life. If life exists as close as 124 light-years away, there could be millions of inhabited worlds in the Milky Way. The Fermi paradox becomes even more puzzling. The question, where is everyone, gains new dimensions in light of potential life on K2-18b. If there are millions of life-bearing planets, why haven't we received a single signal from any of them? Perhaps advanced civilizations use communication methods we cannot detect. Instant communication based on quantum entanglement or gravitational wave messages might be possible. The Great Filter theory is both hopeful and terrifying. According to this theory, the probability of life reaching an intelligent level is extremely low. At what stage of this cosmic filtering process are the microorganisms on K2-18b, if they exist? Is life present but the beings not intelligent? Or are they intelligent and silently observing us, ignoring our presence? Or have they simply not discovered us yet? Perhaps the Great Filter is still ahead of us, and we are the first species trying to pass through it. The Kardashev scale classifies civilizations based on energy consumption. Type 1 civilizations use all the energy of their planet, Type 2 harness the energy of their star, and Type 30 utilize the energy of their galaxy. Potential life on K2-18b may still be at Kardashev level 0, essentially at our early 1900s stage. Could it be that they cannot contact us yet because we are living at a much later stage than them, or because they simply haven't advanced enough? SETI, Search for Extraterrestrial Intelligence efforts are focusing on K2-18b. Plans are being made to send mathematical signals similar to the Arecibo message, but a distance of 124 light-years means a 248-year round-trip wait for communication. So if you sent a message, the reply would likely be received by your grandchildren's grandchildren. The Breakthrough Listen project is searching for technological signals from the K2-18b system. Fast radio bursts, organized optical pulses, and traces of industrial atmospheric pollution are being scanned. With the James Webb Telescope, detecting artificial atmospheric compositions is now possible. CFC gases and industrial byproducts could be observed. A paradigm shift is happening in astrobiology. Beyond carbon-based life, silicon-based, ammonia-based, and even plasma-based life forms are being investigated. K2-18b's hydrogen-rich atmosphere requires metabolisms different from those on Earth. How could we communicate with beings whose basic needs are completely unlike ours? Universal biology principles are being explored. The panspermia hypothesis is also gaining renewed attention. The possibility of life spreading from planet to planet seems more plausible with the discovery of K2-18b. Lithopanspermia, transfer of life inside rocks, or radiopanspermia with radiation-resistant spores, could have created a galactic network of life. Perhaps we share the same ancestors. The rare Earth hypothesis is being challenged by K2-18b. This hypothesis claims that Earth's conditions are extremely rare: large moon, magnetic field, plate tectonics, Jupiter's protective influence. However, the biosignatures on K2-18b show that alternative habitability models are possible. Could Earth not be the only unique life-bearing planet in the universe? The search for technological signatures is intensifying. New methods are being developed to detect megastructures like Dyson spheres, artificial light pollution, signs of atmospheric terraforming, and interstellar probes. Infrared excess measurements of K2-18b could reveal industrial heat sources. Analysis of waste heat signatures is revolutionary. The zoo hypothesis is even more unsettling. According to this theory, advanced ET civilizations are aware of our existence, but choose not to interfere. They are observing us in a cosmic zoo. Would you be uncomfortable being watched by aliens? Or if their intentions are good, would you feel protected under their observation? They might be following prime directive-like rules, as in Star Trek. The simulation hypothesis gains interesting dimensions in the context of K2-18b. As Nick Bostrom suggested, we could be living in a simulated universe, and life on K2-18b might also be programmed parameters. Digital physics and computational universe models support this possibility. What does it mean for life to be digital? Multiverse implications cannot be ignored. According to the infinite universes theory, our universe is just one of the life-friendly parameter sets. The discovery of K2-18b supports the anthropic principle. Our universe appears fine-tuned for life because we can only observe universes where life exists. From an existential risk perspective, K2-18b represents both hope and threat. The possibility that the Great Filter lies ahead makes risks like nuclear, war, climate change, and AI alignment problems even more critical. What is the likelihood that one day these civilizations might destroy us? Planetary protection protocols become even more important. The cultural and religious implications are profound. Life on K2-18b creates theological challenges for monotheistic religions. Even the Vatican has developed a theological framework for extraterrestrial life. Concepts of cosmic purpose and human specialness are being redefined. If life turns out to be widespread in the universe, how would you cope with that? As Carl Sagan said, If we are alone in the universe, what a terrible waste of space. K2-18b might show that this waste does not exist, or could this vast space which we see as wasted actually have a more special purpose? Is K2-18b the beginning of a cosmic awakening? We are eagerly awaiting the solution to the Fermi paradox. With these major discoveries, what exactly do we want to leave for future generations? Our answer may become clear in 2025. With the next observations from the James Webb, we could reach 994% certainty and declare a 5 sigma discovery. Then we will truly know we are not alone in the universe. These videos are created with immense effort and go through many research processes. That's why your support means so much to me. Don't forget to like the video and subscribe. Thank you in advance and see you in the next video.